Perfect.
Yes.
Okay. At any time, if there is an issue, just shout.
Sure,
Okay.
no,
Thanks,
no,
everyone. So the talk has already been introduced. So basically, I just want to see, to show how we moved from old closed system towards some more and more opening of the network, and then where our work stands in there, and what do we see as coming next. Just brief introduction. So as Ivan said, as I'm associate professor and fellow Trinity College. I'm also in PI for Science Foundation Ireland and in two of the SFI Center and so on. My work has really been around, let me get, actually I want to get that pointer, but I'm not sure I can. Can you see my mouse when I move?
Yeah, we can see it. We can see it.
Perfect.
It's perfectly visible. Yeah.
Yeah. Actually, I have it here. Yeah. So, so I've been working, and I will show today, in access network virtualization has been one of the main topics. And then when the last 3-4 years, also opening on disaggregated optical networks, worked on fixed mobile convergence, and always we keep an eye on experimentation. And in fact, recently we started to build a large testbed on this. I just wanted to show a little bit the research group, people who actually do the work. So that's kind of a snapshot of what's at the moment with 4 open positions. 2 of them, this is a US Ireland project that Dan has put together when he was still in the US. And that's on this SDN control of quantum networks. So it's looking for people in there as well. But you can see the different areas and the different people involved. So the summary of the talk is going to be about really main three points. So one is about this open networking trend, how it has evolved, where it has evolved. Then from there, I'm going to link to our work on the point virtualization. And this is really to show, how many things you can do once you virtualize something. So once you move it into software, how much does it open up the whole things to research. And then just finish at the end towards see, how can we go to this concept of digital twin, and what does it mean, and what are the steps that we're taking towards that direction. Okay, so network realization, open networking. I mean, we can see today that the open networking is really anywhere. And when we see everywhere, I mean, we're also meaning commercially everywhere, because 10, 15 years ago, we could have said that, but it was really on only small research type of infrastructures. But today, I really see it across the wireless, the telecoms central office, and recently on the optical system. So what does it mean to virtualize the radio? I mean, they can give tons of definition, but one of the most efficient, I think, is going from a radio built on a circuit board to a radio that's built on software. Okay, and GNU radio has been there as one of the first ones to have done this, and it's been there for like quite a long time. And of course, the flexibility is huge, and that's the reason why we see today is coming also into commercial system. But of course, you have the flexibility that you can adapt, for example, transmission formats, depending on the environment, because now you can actually write a reactive software that, depending on the environmental condition, you can pretty easily make a decision. And you can make a decision with a software, with an expert system that says, if this happened, then do this, if this happened, then do this. But we have seen that recently we are really start borrowing from the areas of machine learning that have been applied to other fields and are being brought into networking. And again, the softwareization was a big, it was a massive step towards enabling the use of this type of algorithms. Other interesting thing you can do, you can coordinate with other radios, because you can have, you can build a back communication channel and tell what radio each other is doing. And again, build a software not just for the radio, but for the interconnection of radios. And of course, you can integrate with any other software components that you may want. You can create a library, okay, of components. Now, this was things that we've seen with the GNU radio. So normally it was just academics, playing a little bit with that. Some industry as well. But then, last 10 years, we've seen that software has also been built for actual LTE base station. So today you can run no problem a 4G base station from a laptop or on a server. And the last year, you can also do that on the 5G new radio. Now, what does it mean? It means that you're going from the situation on the left, where your base station is a piece of hardware, so telecom grade piece of hardware built by one of the 3 or 4 vendors that can do that. The idea is that you move that into so you decompose it, you disaggregate it, you turn the hardware into piece of software, and then you run your software into server. Okay. And the only thing that you need is that on the right hand side, you need some kind of hardware that basically does the radio frequency part. Okay. And that's really all you need. You can even substitute the server from a laptop if you're not looking too much into performance. And that's really has happened. That's one of the latest trends that you've seen real for mobile base station. And there are base stations today that are actually built this way. Now, of course, this example, okay, the first example that came out is where the hardware only does a radio frequency part. And it means, for example, if you're looking downstream, what it means is that this hardware does a sampling of the radio waves, and then it just sends all the samples of the radio wave up to the server, and the server does all the processing. That's the way, like if you take SRS radio, normally that's the way that the system was built. Now, because people have been interested commercially to that, now this has been brought into the standards, and then the standards have been looking at other, I don't want to say more effective, more efficient ways, because each way has its own advantage and disadvantage, but other ways of doing this functional, what's called functional split. So the idea is that, do you really have to split here where you have radio frequency, so only the radio on one side and all the processing on the other side, or can you split in another place? Okay, so if I split here, for example, I'm going to do radio frequency as some of the physical processing on one side. That side is most likely going to be just hardware, and then all the rest be done on software. Now, there are, as you can see, a lot of options. Okay, in fact, the standards initially have decided to do a lot of options. And what basically you get, basically, I think the fundamental, because I don't want to go into the details of all the splits, is this: that the more you split on this side towards the RF, okay, that means the more you simplify your antenna side. Okay. Now the drawback, so the advantage is that the antenna side is very simple, because at best can just be a frequency converter with an antenna. Now the drawback is that the link, so if you separate this, then you need a link that connects those radio frequency to the first step here. Imagine this is in a server, so you need some kind of communication between the two, and this is not going to be in the box, this is going to be outside communication, which most likely going to have to use fiber. So if you do that very high here, okay, in the options with the high numbers, now you're gonna have a huge amount of capacity requirement, because you're sending samples of a waveform, you're not sending bits really of information. And this can be a factor of 30, can be easily a factor of 30. So you multiply the cell capacity by 30, and that gives you how much capacity you need here. And also you need a very low latency. Okay, I'm not going to go too much into details of that reason. I can tell you later if you want to know. And then as you move toward this side, instead, what happens is that, well, you're moving more and more towards the concept of the distributed base station. So you're going back to the whole systems where all the base station intelligence was the antenna side. So that's the disadvantage, is that you get the antenna side more and more complex. The advantage is that that transmission link that was very hard to satisfy here, the requirements were very difficult here. Here it's pretty simple. So you're at the same cell rate as the cell, so you don't waste any capacity, and your latency, is maybe on the order of 5 to 10 milliseconds. Of course, there's another advantage of doing the things I had mentioned here, is that if you do everything here, your processing is all centralized. So if you have more than one base station, then you can start thinking of synchronizing the way the base station operate directly into the centralized location without having the antenna side to communicate, which is a big advantage. Now, so you can see, so there's a lot of options. Now, if you want to commercialize that, you can't commercialize all the options, okay? So the idea is that you pick one and then you focus on that one. Because already going from this to this, it's a big, it's a strong, it's a big step for companies or industry and vendors. So the idea is that there was an Open RAN consortium that was built in, and the consortium did two things. The first thing that they said, the 7.2 is the split that's going to be used. So 7.2 is basically inside here. So take this low physical layer and split it again into two. So that was decided, and once you decide that, then you can say, okay, now you tell who develops the remote unit, which is the hardware part with the radio frequency. You can tell them you have to develop these specifications, and then everyone else has to develop the specification, and then they decide an interface, and that's the open frontall interface. Now, in addition to that, Open Run has done something even more interesting, which is define a complete architecture for the control of this mobile system. And they have defined what's called the RIC, Radio Intelligent Controller. More than that, they define the interfaces. And the idea is that all the control interfaces are defined. Okay. The idea is that now you can write software, you can write your own software once you have the interfaces defined to control the base station. And this would be a talk on itself, discussing all of this. The point I think I want to make here is that it's really opening up the base station not just at the data plane, but also at the data/control plane, because this, depending on how fast is the control loop that you choose, here you go anywhere from direct data plane, control plane, and management plane. And the idea is that now you have for the first time open interface to write software for that. Now, this, of course, has been, if you look at an architectural perspective, and again, here the same split that I mentioned before, this just defined that the part on the right-hand side of the split is called the remote unit. And then everything else is software, and that the software is divided in a distributed unit that mostly take this part, and the centralized units, which also take this part. Now, the centralized unit in principle can control multiple distributed units, and that's the reason for the name. And the other things is that now you can put them in different types in a physical architecture. So you could have a remote unit only at the antenna side, and then you have a connection towards your first computational node. Or in some cases, you can have the remote unit and the distributed unit on site, and then you have the centralized unit here. So you can see there's a myriad of options on the way you actually locate the different parts. Okay. And now this brings interesting things. I mean, the reason I'm showing this is really that it's about these interfaces. Okay, so these are, it's about these connections. Okay, because now it becomes extremely important which way you create this connection, and I'm going to show you later on why. Okay, so this just want to say that's what's happening on the wireless, wireless network or mobile network perspective of domain. Now, something similar has happened recently on the optical layer, and that's something that no one really believed would happen, because I mean, at least with the radio, the GNU radio been there for 20 years, so people kind of saw, you could do that. But at the optical layer, has been a very closed system for a very long time, and no one really thought this might actually happen one day. But of course, if you do it in all the other parts of the network, of course, someone is going to push it also on this side. So what does it mean? I mean, from anyone from the, let's say, maybe from the Ethernet side, this could be a shock. If you take an optical network, the standard way of building the optical network is that all the components come from the same vendor, as well as the system, the line control systems, okay, and the control system. And this is one of the ideas that if you take Ethernet is digital. Once you comply to the standard, it's digital. So you have to satisfy whatever are the control plane messages and the protocols. But once you do it, that's it. An optical transmission layer, you're on the analog domain. Okay, so now be compliant on the analog domain is not as straightforward as in the digital domain. Okay, there's a lot of things that can happen that you can really control. But nonetheless, the concept of opening the optical layer is really going from a place where all your equipment is from one vendor and all the interface are closed. So this can only be controlled by the software from the same vendor or so on, or another vendor that has an agreement with that first vendor. Or else, the change here opening up is that design the system in a way that you can mix and match every component, okay, take a component from any different vendor. This is like Ethernet is built at the moment. Now, the key thing to do this is basically opening up all the interfaces, because once you do that, you also need a controller, an external controller, control plane that can control all the different heterogeneous devices. Okay. Now, well, of course, we're not, commercially, we're nowhere near this yet, but there are things that have been opening even commercially. Now, what are the pros and cons? The pros is that you open the market for component to multiple vendors. So then it means your costs can really go down. You have no vendor lock-in, which is a big problem for operator. Okay, so, you can buy basically the latest technology from the later vendor. That's something you can do if you do this, and this is not something that you can do in a closed system. And then, I mean, the other interesting thing is that you softwareize the control plane, okay? And once you bring it into software and you open it up, you can do a lot of interesting things. It's not just the design of the specific system, but you can integrate that system with a different system as well. So you can you can converge, maybe a wireless and an optical system. You can do a lot of that with programmability. I mean, what are the challenges? The challenges is that the system, as I said before, is analog and is open, so the behavior is not fully predictable. And while in a closed system, you can control more of the variables. In an open system, you cannot do that. Okay, so this brings some issues in terms of margins. And what does it mean? I'm going to go quick here. Don't want to spend too much time. Margin means that if you got an optical network, you have an idea. You make a plan or a calculation on how much, for example, power you need, transmission power you need by the receiver, or how much optical signal to noise ratio you need to get to the receiver. And you make an estimation on how much power, how much distance from an amplifier you need to get there, and you work with that. Now the margin is there because the calculation might not be correct. There could be things that you haven't considered. There could be aging of the components and so on. Now, if you know your system very well, then you can keep your margin smaller because you know more or less how the system is going to behave, all the components perfectly. If you don't know that, then you need to have more margins. Now, this slide only shows the pros and cons of having margins. So if you go towards more aggressive margin, that means you put the margins very low, you're going to reduce the capacity of your network. And the reason is that you're going to attempt optical paths that end up not working out. Okay, and that's basically wastes capacity in the fiber and reduce the capacity of the network. They say, okay, what if I'm more conservative with the margins? Say I get higher margins. Well, if you get higher margins, now all the paths that you try to set up, they will work because you're being conservative. But there's a lot of paths that could have worked and you didn't even try. Okay, because you thought they wouldn't work. So at the end, there is an optimum point, right, where you should be with your margins. What's the problem with that? The problem is that you don't know where that is, and also this is different for different links. And these are just some examples that, some studies that were done by, can't remember the company that did this, but basically showing that you could actually do this open networking in the access because you have like a lot of margins, but if you move to the core, it becomes a little bit more critical, so you don't save as much money. Okay, so that's the optical, and then the other domain where we have seen opening the network, and I think today this is probably was being one of the first, even before the mobile network, is on the layer 2 and layer 3, so the switching and routing. So just to show, before this centralization concept and virtualization came up, you used to have the common distributed routing protocols. That means that, for example, you have routers that send information all to each other, link set information. They run, each of them run independently an algorithm. Once that algorithm converges, they fill in the switching table or routing table. And from there on, from the moment that's converged, your system is stable and you can route packet. Now, the centralization of this, you can call it SDN, you can call it separation of control plane and data plane. What really means is that means those now hardware switches, they don't run the protocols at all, okay? They are just fast silicon with an empty routing table. So you need another intelligence to fill in that routing table. And that intelligence now is centralized, okay? It's a server, and that server does all the calculation, route calculation, all the route optimal allocations. And once it has decides which are the routes, it basically pushes the information into the switching table so that from that point, all the switches or router can do fast routing by themselves. That's the idea. Now, of course, the advantage is that, if you have a complete view of your system, you're going to be making much better routing solutions that, if your system is completely distributed. Of course, now you cannot do this between autonomous system, BGP, because there's not one entity that controls the whole internet. But, within your own network, this, seems to be a much more efficient solution than this one. Now, as we talk about this, this is kind of, we're talking about data center, we're talking about the internet, and the next thing is the telecom operator. And the programmable operator is kind of across all of this, but specifically there's one place which is really the domain of the telecom operator, which is the central office, okay? And that's what offers access system, mostly fixed access system. Now, it's an interesting thing that now the concept of open flow and SDN, they kind of moved to also go into this central office, which historically has been extremely close because, it was really the stronghold of the operator. What does it mean? Take, for example, a fiber to the home access system. They're mostly developed to this technology called passive optical network, which use passive splitters. It's kind of a broadcast and select system. And you move to a place where you have, your GPON. GPON is just one of the PON standards. The optical line terminal, which they actually terminate the signal. Then you have the Ethernet aggregation, the broadband network gateway. Okay, you have all these proprietary devices. And this central office re-architected as a data center, it kind of said, if I had to open up all these devices, I find two things. I find a switching component, packet switching component, and then I find some software. So why don't we reorganize this and we build into a data center, which is a bunch of switching, fast hardware switching components, and then servers to do the calculation. And that's really what has happened. And I think every operator on earth has actually tried, at least tried this. I can't say that they're in production. I guess there are going to be some of them in production, but this core is still evolving. So for example, one of the latest embodiment was this SIBA, SDN-enabled broadband. And more recently, they're also going into the convergence of the edge cloud, so the MEC cloud, and this project is called Ether. So that's been extremely interesting because it's really changing the way people see the network. Now, one thing, guys, I'm going to link here to the work we did in the last 5 years. So if you look at this, this is about taking this PON and building it into software. However, this solution was kind of built for the residential type of services. Okay, the reason is that if you see this PON, the scheduler of the PON is actually still on hardware. It's like kind of a pixel box. It means it looks like an Ethernet switch. The only difference is that the ports are PON ports instead of being Ethernet ports. But that ports, so that switch also does the scheduling. Okay. Now, is that a problem? It's definitely not a problem for residential. And I think this is really good because you can create multiple instances. You can have from the same infrastructure, you can instantiate multiple virtual network operators. So this works very well. But the scheduler is still, there's one scheduler per port controlled by the hardware, and you can't really make many changes in there. But if your latency, if you're looking at giving broadband where your target is to, I don't know, to give 100 megabit per second, and with the latency maybe of a few milliseconds, and especially a control granularity that says, you average that every 5 or 10 milliseconds, you check your bandwidth and you make sure that the person gets 100 megabit, that's totally fine. Okay, but we'll see now that as you move into 5G, you're not building this only for residentials, you're building for other services, and the type of control that you need here kind of changes a little bit. So that's where we go into the part that I'm going to talk a little bit more about the work that we did in the last 5 years. Now, as I was saying, this core virtualization, first of all, don't take me wrong, it's been a great idea, has worked well, and is still working well. But is that enough for passive optical network? So what I was to say is that, yeah, if you're a residential user, residential VNO, this works very well because it gives you the bandwidth that you need, and it's checked within a certain number of milliseconds. That's fine. However, if you're trying to do this for things like fronthaul of your network, it doesn't really work, okay? Especially because fronthaul, has a very strict requirements in terms of latency. You're talking about 100 microsecond. And so the fact that you give me, even you give me 1 gigabit, okay, and the scheduling capacity assignment is averaged over a few milliseconds, that doesn't really work anymore, okay? So in fact, I will see later that here you basically need to control the scheduler. If you want your front base station, like the 7.2 split around that I mentioned, if you want that to work in a PON, you have to control the scheduler. Okay, because you have to make sure that there is the minimum amount of latency from the moment a packet gets into the base station to the moment it can actually leave to go up. Okay, I'll give you more detail about that. Okay, so but again, this in the chord, if you look at chord, the dynamic bandwidth allocation, which is the scheduling when you go upstream, then that's really the problem for the PON is upstream scheduling, because it's a point, multi-point to point, which requires centralized scheduling and introduce latency. So that's a problem. So what we did is, well, why don't we move further and we keep virtualizing? So that's really all we did. So we go from a system where the scheduler is within the physical part of the OLT. So it's actually in the hardware, to a place where we move this outside of the hardware, okay? And we build it in software. So how do you make that work? So normally, the normal operation is that there are these ONUs send messages saying, oh, I need capacity to transmit upstream. In this system here, all of them send to the same place. This makes calculation, and then it sends a bandwidth map that tells this is exactly when you can transmit next time. And that's the problem that takes 1 or 2 milliseconds. Now, the way we did it is that we virtualized it. And once you virtualize, the interesting thing is that if you virtualize something, then you can create multiple copies of that. Okay. So now the idea is that if you create multiple copies of the scheduler, you can give a scheduler to a virtual operator. And these are completely independent. You can give the scheduler even to to a control plane of base station, so that the base station now controls when is the PON scheduling coming up. And again, basically we divide it in two. One part is called the merging engine. One is actually the virtual DBA. You can have more of them. And as these guys send the requirements, each of them makes his own calculation. Each of them comes with a virtual bandwidth map saying, this is my calculation on when this guy should transmit. But then you have to make it backward compatible with the PON. So what you need to do is that you need to merge all these requests into one, and that one is sent to everyone else. Okay, so that I can at the physical layer, you're still sharing the fiber. Okay, so this cannot make autonomous decision. Now, the interesting work here is really on this merging engine, and that's where we're focusing for the last year or two. How do you optimize this? And I'll show one example on the slides. So the only interesting thing is that, we had a patent on this. So the patent and the concept was also included in 2 standards. So from the broadband forum, this is TR402, TR370. And I mean, this really was only possible because we got a very strong support from Vodafone and from NTT, because NTT is also looking into this direction, very interested in that. So we also then had Intel got interested as well, because of course, if you can bring this, if you can build a PON in software, you basically means you're gonna tell an operator he has to stop buying, I don't know, Nokia equipment, and you should start buying Intel processors, right? So of course, it's a big business, big interest in there. So Intel came up and were very interested. And at the beginning, they helped us a little bit using the DBDKs, but then they got very interested and then decided that they will build a standard compliant passive optical network. So basically, they built all the blocks, including some part on FPGA, that really produce a standard compliant 10G passive optical networks. And then we basically hooked up. So that was for us really the opportunity to start hooking up our software into that, so that you can replace the normal PON scheduler with this concept of virtual DBA. And then we are still working with Intel. We just had a new project funded from them. Now, interesting just to show that they actually had this in 2 splits. Okay. Now the split here is only about physical layer. Sorry, it's kind of about physical split. Everything remains in the same box. Okay, it's not like the open split. The only difference is that they knew that the processor might not be able to do all of the processing, especially when you look at the framing, the cryptography, and so on. So there are two versions of this. One where these mathematically intensive operations, and I mean these are not intelligent operations. They're just framing and reassembling on the frame. So they're kind of really dumb operation. So they decide one version, we're going to do this on FPGA, and then all the other interesting intelligent stuff in software. And also of course, our scheduler is always in software. And then there is another version where say, okay, you know what, let's try anyway to do all of this in software, where there is no FPGA at all. So the only thing you get out of the Ethernet, your Ethernet card in the server. And yeah, so this is basically, so the results is that, okay, if you put the FPGA, you get 10G, no problem. Okay, that's fine, that works. If you don't use the FPGA, so these are the results that were obtained. I think these are now probably 1.5 years old. Okay, so you basically get half of the capacity in the upstream and maybe 75% on the downstream. And again, this is because that it is mathematically complex to do this for a processor. But this was before their latest Xeon, and now I think the plan is to try it again with the new Xeon, because the new Xeon was built on purpose to have some optimization that is very useful, especially the networking ones, networking Xeon for this type of functions. Okay, so anyway, it does. And I mean, it becomes very interesting because even, you have a processor today with multiple cores, so you can really assign each core to a pawn, or maybe each couple of cores to a pawn. Okay, so a processor with 30 cores, you can build 15 pawns in there. So that becomes very interesting approach to do. Other interesting approach, especially if your multiple passive optical network, they are part of the same fiber network. So you're doing wavelength, multi-wavelength passive optical network. You can actually start considering having not one DBA for each wavelength, but you can have a DBA that looks across more than one wavelength, okay? Because the communication between this is really, really fast. Okay, they are within the same chip. And I mean, it's a lot of interesting things that you can do once you start doing that. Now, just I'll show you an example of that merging engine before. I mean, what I'm showing now is that is really all the interesting things you can do once you move things into software. Okay. And especially, if you have someone that helps you to build it in a standard compliant way. So that merging engine that I talked before, so this really makes a lot of work because it gets bandwidth maps, so it gets scheduling decisions which are independent of each other, and it has to transform it into something that can be stitched together. Okay, so you have to make sure that when you send this, there is no overlap in time, because of course you cannot transmit two things at the same time. Okay, so even if these guys overlap, the solution has to be non-overlapping. And what it means is that you have to move things, around on the time scale. Okay. The only problem is that if you move things around on the time scales, remember this was built to one of the reasons was to keep things really keep the latency as low as possible. So you might end up with a problem that you don't satisfy some service level agreements. And that's where, for one example, the merging engine we did. Now, I mean, we know today that service level agreements are kind of important. I mean, up to now, the service level agreement was more about, you go to, a business go to an operator, it says, I need a 10G link with a certain, I don't know, certain availability, and that ends up in there. But as you move into 5G, you can see now that, you might need an SLA for even a small cell if you want to do it over a PON. So this is going to go a lot more than, it used to be. Now, how do you do this? Okay. Now, basically, I mean, the way we know how to do it is through prioritization and queue management. Okay. And it's basically based on one thing. There's a lot of, you can do a lot of fancy algorithms, but the ultimate decision is about who goes first. So you have multiple queues. The ultimate decision is just one: who goes first. Okay. Now, if you can think this, that's the way it is, and I think that's the way it will always be at the data plane. Okay, so at the data plane, when you have the multiple queues and the hardware has to decide which queue to pick from to get into the port, is always going to be, most likely, it's always going to be based on that. Okay, that's the only way to do it. However, that's not the way you should think when you do the high-level decision. So that's the argument. Okay, today it is though. So I mean, today you actually configure the queues with a certain algorithm that is going to pick that before the other one. Okay, so it's a bit like the thing that this one is a bit like programming in assembly versus programming at a high-level language. So you don't want to use the assembly, right? So you want to use the high-level language, and I think you don't want to make your decision just saying who goes first, because you haven't got a clue, who should go first. That's the problem. For example, I mean, it's easy, okay, if you say, okay, voice has to go before video, blah, 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 okay? But if you go more into details of the different type of services, that might not be that clear anymore. For example, let's say you have a service that wants 95% of packets within 100 microseconds. And you have another service which was 99% of packets, but within 200 microseconds. Now, first of all, which one you pick first? Okay, it's not immediate to know that. Second thing is that you can't even say that one is more important than the other. They might have the same importance. So that's the other issue with priority. So what we did here is build an algorithm that takes instead of taking prioritization as a decision mechanism, it takes the probability of breaching an SLA. So every time there is an overlap within the requests, something has to be moved. Instead of saying one is higher priority, you basically look at the packets. You have to keep a state for the packets, but here you're not in the core, you're in the access network, right? So you don't have billions of flows. You probably have hundreds maybe of flows, so it is feasible. So you look at, every time you make a decision, you look at what is the history and what is the chance of breaking any of the SLAs. So you make the decision that minimizes the probability of breaking the SLAs. And these are just some examples. So if you base your things on priority, you can see different flows here. They would have different profiles or different size, but they're all important. And of course, if you do priority base, you can't have to give priority to some of them. And that's what happens, is that you will see that automatically some of them will keep better for a higher percentage of load, but a lot of them will go down very quickly. However, if you instead of basing the priority, you base on SLA, you can see that they're kind of the same here. Okay, that means that of course maybe you go up to 60% here, but all 60% for all of them. Okay. And I think that's important because, in this case, you don't want to say that one flow is more important than other. They're just different. And that's some of the work that we will be able to do. Now, one other thing that I mentioned before is that if you have this new frontal system from mobile station, so Open Run or Cloud Run, you cannot transport them over a passive optical network because they have latency constraints. Yeah. So they have latency constraints because of some automatic repeat request that's built into the protocol. So that has to be done within a certain time. I think it's about 3 milliseconds. But 3 milliseconds includes all the times of air propagation and processing. So basically, the optical guys were told, if you want to transport a frontal over fiber, you need a one-way latency over the fiber of 100 microseconds. Okay. So first of all, that limits the transmission, of course, but that's okay. The other thing is that it's very hard to run any scheduling within 100 microseconds. Okay, so normally this is what happens. That the BBU, so this BBU is think of this about the DU. Okay, it sends the scheduling message to the handset to tell when you are able to transmit upstream. At that time, when that's possible, the handset will transmit the data. Now imagine that the remote unit that we discussed before is together with the ONU. So that transmits the data, that goes in there. Now at this stage, kicks in the second protocol. Okay, so the ONU now has to wait for an opportunity to tell the OLT that it needs to transmit information. The OLT needs to make the calculation for all the ONUs, and then it sends that bandwidth map that says to the specific ONU, you can now transmit. And there you go. Now notice this is the all latency, but a lot of it is actually due to the protocol. Okay, it's not transmission latency. So what was done, NTT proposed this first, and then now it's been standardized, is that when the BBU sends that message to this unit, basically the OLT spoofs that message. Now, when I say spoof, what it really means is that now there is an interface by which the BBU can tell the OLT that something is going to happen somewhere in the future. Okay. Now, because the BBU knows exactly when the handset will transmit, because that's the purpose of the scheduling from the mobile side, he knows that he can estimate very well when this point is going to happen. So the BBU is going to tell the OLT, expect that there will be a request, high priority request from my base station, from the handset, from the base station at this point in time. So the OLT can start doing the processing. It doesn't have to wait this point here to do the processing. It can start the processing straight away. And by the time, basically, it schedules the capacity so that the opportunity to transmit arrives just before the packet arrives in here. And that means that then there is no latency here. So all of this completely disappears. And this can transmit. And it's been shown that you can get below 100 microseconds if you do that. And this is the only way you can do frontal over PON. Okay, it's been standardized by the ITU now. Now that's interesting, and that's perfect. That's the way you do it. Now there is another case, which is you need low latency because an application needs low latency. Now notice that here the application, we're not discussing about low latency application. Okay, we are discussing about low latency of this specific wireless service. Okay, the application sits on top of that and will have its own latency depending on the whole system. But the idea is here is that you can only do this because the BBU here knows in advance, because it's scheduling it, when this packet will arrive. Now, what here, if here, let's say you have another distributed application, maybe running on Wi-Fi, and you have no idea when this is, okay? Well, then you're on your own, okay? You can't use this protocol anymore. And there is a lot of work being done at the moment in trying to reduce that latency when you cannot know when the packet arrives. So we did, again, because of this programmability, we did an interesting approach here. So what we did is that this is specifically valuable for virtualized system. And basically we recognize that in a system, in a virtualized system, you're going to have some kind of a network card, and then you're going to have your process inside. So the idea is to split that capacity allocation into two. One that occurs on the line card, okay, and one that occurs on the processor. I'm not going to go into too much details here. I just want to show you the concept. What does it mean? It means that the ONU request for a capacity here, the message, there are different ONUs. Some of them will be low latency requests. Some of them will be normal. So this card here, and this is, so basically we wrote the P4 program. So this is, we modified the data plane so that we provide the programming before. This request comes here. Sorry, this is a demonstration. So this is actually the packet generator. These are the ONUs that generate. So this is the network card. Okay, this is the network card, and this is the processor. So the request goes into the network card. The network card says, okay, if this is a low latency request, I'm going to take the request. I'm not going to send it up. I'm going to have to take this and put it aside. Then, in the meantime, all the other requests goes into the software, and the software keeps doing its scheduling. Now, you have to think of this as a stream of multiple frames, because the idea is that, let's say each frame is 125 microseconds, but this software process and everything could take multiple frames. Okay, it could be like 300-400 microseconds. So the idea of spoofing that information there is because you don't have to wait that this whole process goes across the 300-400 microseconds to generate the actual bandwidth map. What you do is that you take the first one that comes down. Okay, this bandwidth map might have come down from requests that came like 3 or 4 frames before, but you basically take the first one that arrives, so you don't wait any time. You wait a few microseconds, and then you modify some of those requests to put your higher priority. You can do it in multiple ways. One way is that you leave some of the bandwidth map here unallocated, and it's not efficient, but at least you can spread that lack of efficiency across all the nodes, all the ONUs. Yeah. Or else, you can think that you can preempt some of the lower priority and so on. But basically, so the implementation, for example, you could look at if you do the DPA, normal DPA, your best latency is around 400 microseconds. And if you do this mechanism, you guys will get an average, not the best case, actually average of 237 microseconds. So, it's almost twice faster. 50% faster than the other one. And this is just, again, interesting things that you can do once you program it. One interesting thing, one further interesting thing is with regards to the edge connectivity problem. Okay, what is that? Now, I'm focusing on passive optical network, okay? And one of the reasons that I'm focusing on that is that it's kind of the only way that you can bring a lot of capacity to a lot of places with a way that's very cost effective. The other way to do it is point-to-point fiber, but depending on how much fiber is in the ground and how much money you can spend on the lease of the fiber, a lot of times for small cell, that's not viable, okay? While passive optical network has been used for residential users that pay €50 a month of fees, so that's definitely more viable than spend 10,000 a year on a leased fiber. So in any way, one problem with the problem that works quite well. It's a north-south protocol, so it goes from a central office downstream, like in a tree structure, and then it goes back upstream. Okay, now that works very well. Okay, we can see we have the protocols to run the remote unit and the distributed unit. So you can do residential, you can do mobile services, and so on. However, recently something else happened. People start putting edge nodes into the network. Okay, now that's the edge node. If you think about it, it changes a lot the whole architecture, because now if you put an edge node here, you want to communicate directly. There's no point of the communication path going back to the central office and then to the edge node, because otherwise you might as well put the edge node in the central office. Yeah. Now this is non-trivial because you basically, this edge node might want to connect to multiple entities. Okay, it might have, it might host the distributed unit for those base station, but it also might host services for the, for residential or other things. And so you need to activate this communication pattern. And that's very hard to build a mesh network in an access. Okay, I mean, unless, of course, you have no money constraint, then you can do everything. So, and another thing that I want to show is that, of course, I mean, the use case, the typical use case we always say is about the distributed unit. So you build a base station and you want low latency. So you have the remote unit here and you distribute units somewhere in the edge. And this can be shared across a number of base station remote units. Okay. But there's also something else. I mean, think about high performance VR today. There's two ways you can do it. And this is just a simple object recognition. You can either have, some kind of big headset with processing plus big processing node in your home, and then you have to stay at home because you can do that nowhere else. Or else you get something which is very lightweight, but also, you need quite a lot of processing, and it takes processing from the network. And just to say, I mean, even today, I think I read last week that NVIDIA now has a lot of GPUs that are remotely accessible so that you can run like high performance gaming without having a high performance GPU. So that's really happening, right? This is some work that some colleagues, I wasn't involved in this, but some colleagues did, for example. And, it's a simplified version of that. And that says, what if you have a small amount of processing locally available and you want to do image recognition? So these are like a Raspberry Pi, for example. What if you can do it locally, but you only have a little bit of performance? Or else you do it over Wi-Fi and on a laptop. Okay, so you basically have to go to the transmission system, but then you have higher processing. So the results was that, the average time, if you were doing this type of recognition, was 2.5 seconds versus, 0.2 milliseconds. 0.2 seconds. Now, of course, in object recognition, that means something that can be usable versus something that cannot be used at all. Okay. And again, the interesting thing is that the more you can spend on that processing, the more accurate you also get. Okay. So it is important then that you enable this communication. Again, you can do Ethernet point-to-point mesh, but that's, I think, for the access out of the question, the cost. Or else another thing you can do is try and modify the PON to do this. Now, Nokia has been doing that for quite some time. I mean, at least the concept, none of this is commercial. And it's about modifying the splitter location so that you can send the signals back. And the idea is that from here, you can send a signal back. Okay. And yeah, but this is interesting. They're all fully passive solution. It means these splitters still remain passive. The only problem with that is that, if you're completely passive, you lose flexibility. Now, the work we've been focusing in instead of is take some of the splitter and make some of the splitter active. And by active means that you might have some components that are powered. Let's put it this way. Okay, so they're not digital components, as in you don't do any packet processing, but they're analog components. But you might want to select a certain wavelength reflection or have an amplifier. And the idea here is that you can get some of the channels and decide which channels should be reflected back. So you can take one communication channel that then gets broadcast again across all of them. And it's good when you think about this and you can mix that with the virtualization, which now means you can basically, with this concept and the virtualization concept, and now you can build a group of communicating entities which are even not within the same split, low-level split of the PON. Okay, they have to be at the end within the same PON, but basically you can get 3 nodes here, 2 nodes there, and any of them in principle can be your edge node for the computation. Okay, so that's interesting thing, and we've done this some. theoretical analysis, simulation, but also we tried to see whether this is actually possible because of the reflections. And yeah, I mean, it all works quite well. And I mean, the extension there is that, you know, again, the interesting thing is that when you start mixing up this part, which is pure access, sorry, I got someone, so I got a call. Sorry. Okay, so when you mix this concept of the access, you mix it with the metro network, and all of this flexibility, all of this capability of hosting edge nodes, you put it together with the optical connection to the data center, and sorry, and to the central office and to the data center. Sorry, this is annoying now. I'm gonna have to turn off the system. Just 1 second. Sorry, 1 second. To power it off. Okay. Okay. So I was saying it's interesting now because with this, we put all this concept together. So now suddenly you have a highly connected access, which is transparently connected to the central office, and then possibly transparent connecting also to a central data center. And the idea there is that, you know, if you can get capacity in your edge node, sure, you get it there. If you don't have that, you can still be able to build a low latency optical connection that goes into a server in here. Okay, it may be expensive, but maybe for, you know, you need it for a number of minutes. So if you have capacity available, you can do that. Or else, and you know, you can even think if that's not available either, to go farther to a data center. Of course, the latency might be higher, but if you can do that all optically, it's only transmission latency. Okay, there is no queuing at the layer 2 or layer 3. And that is to mix all this up together, and then, you know, do optimization depending on the latency that you have, on the load that you have, and then all the application requirements. Okay, now this is just, I know I'm going to be late here, but this is just the last thing that I want to show of interesting thing that we've done by this programmability. It's a demonstration of optical wireless convergence. Very briefly, I'm just going to say, you know, what this basically means is that we put together the programmability of the passive optical network with the programmability of the wireless system. And the idea here was that if I have a service, okay, an optical service that runs in some network, that optical service could be like a new Netflix service that requires a certain capacity in a mobile network, even in a different country. You need a control plane that is able to instantiate the capacity in the optical network, then down to the access network and down to here. Now, this basically means that you might want to be able to control the data rate of this base station, but also control the spectrum that you use. Okay, this kind of a spectrum as a service, but the idea is that we mix this also with the OLT variable capacity, so the passive optical network variable capacity, and the same as the core variable capacity. So the idea is that, you know, depending on the service that you run, imagine this is associated to a certain area in a city, and you can basically say that the bandwidth of the cells that's used within that location is totally depending on the service that's going to go down that way. Okay, and whatever is not used here can be used by other services. And yeah, there is a demo. Actually, there is here. If you click there, there's also a video with the demonstration, but I just want to go a little bit faster here. I want to skip. And the other thing that we also did, you know, we start playing with multi-tenant PON market. So what if one of the virtual operator has available capacity, is not using it, but he paid for it, can he sell it to someone else? So we start putting this into a economic optimization problem. You know, in which condition this would work, this would not work. It was an interesting analysis. And then we start considering also some of this economic analysis, for example, of the assumption that the system is fair and that whoever does the auctioning of the capacity is not favoring anyone. However, if you go to a real scenario, a lot of times the private incumbent that owns the physical infrastructure, which is the one that would actually run the auction, also is a service provider. Okay, so basically there is no trust. And how do you solve the problem when there is no trust? Well, you stick a blockchain to it. And that was an interesting thing. We basically, blockchain is not as fast, of course, if you want running things at the microsecond. But the idea here is that you do this through the blockchain, and then the idea is that you have everything recorded, and then on the second point, you can actually check whether whether your private incumbent has breached any of the SLAs by getting advantage to his own business rather than the others. And again, this is the last point I was checking here, just to show you there's a huge amount of things you can do once you softwareize these parts. Now, just going to finish now with just the last step. So what would come next in terms of programmability. So here I just want to put this for discussion, and the concept of the digital twin, right? So we have had this digital twin again. The discussion I think is going on at this moment maybe for the last couple of years. And I just want to show what we're doing now towards this direction. This is kind of the ultimate network control, idea that, you move from controlling things manually yourself, which is great, because 10 years ago we couldn't do that. So programmability has allowed us that. But now to basically tell the AI, like, can you actually take control of the network on my behalf and just figure it out, okay? Now, just to break it down, I think, the way we're probably going to evolve, a good path for evolution, just here for discussion now, is, I think that the first step are really looking at get some real, a digital thing, first of all, it has to be bound to some kind of physical entity, so a testbed, okay, because you're basically building a digital version of something that's real. Let's say you got a testbed. So the first interesting step that you can go towards this digital twinning direction is that you start using real input-output from your real network, and you use that to improve the model of your digital twin. So you can think of the digital twin as a network emulation, okay? And the idea is that you can use the real network to get input outputs and basically to start building the model, okay? So you improve the model that you thought was correct, but depending on, maybe it was correct only in certain scenario, certain situation, by having more data points, you can basically use this to improve your model. And that's one step where your simulators are getting closer to the concept of the digital twin. Then the next step that you could consider is that now your digital twin has got a very good model of your network, and you use the input that it gets from the network to predict certain states or anomaly, okay? And it isn't just about predicting that, because normally, if you predict, it means you're still saying that some number are not correct, but you don't know exactly straight away what the problem is. So the concept of the digital twin is that it would need to make a decision on what else to monitor. Okay. Of course, the assumption is that you cannot monitor everything at all the time. So this is that you get something and then you react and you learn on what the problem could be and what else it could be done. What other inputs you need, and you decide that. Now, the ultimate goal is that, of course, of the autonomous decision making means that the digital twin has the right models. It knows what to monitor and when to monitor, and it's at the best point to actually make the decision on what to do on the network. And the idea is that at that point, you basically give your network completely out to your digital twin and say, okay, you go ahead, you know best. So this is actually there's a high level path, maybe it's optimistic, but that's, I think, the interesting way of going ahead. Now, of course, if you want to do this, you need a lot of expertise in machine learning or AI. But first of all, you need a testbed. Okay, otherwise you can't even do the first step if you need a testbed. You don't have a testbed. Now, having a testbed is important. Not everyone can have a testbed. Okay, it's not affordable to everyone. But that's why I think open testbeds are becoming more and more important. Like, for example, the Cosmos that you guys have in the US, and I will also discuss Open Ireland. Now, I'm going to show you what a little bit of that Open Ireland in the last 5-10 minutes, and that's the end of it. And also what are our first steps towards this digital twin. Now, we've built over the last 3, maybe 4 years. That's the work that I've done with Professor Dan Kilper when he was in Arizona. Now he's in Trinity with us. So we have built a tool which is called Mininet Optical. Okay, so it's basically Mininet that I think all of you will be familiar with, but we have had an optical layer so that you can control not just the layer 2 switches. So you have a control plane not just for the layer 2 switches, but you also have a control plane that interacts with the physical components. Let's discuss in a second what they are. But what is the concept of that? The concept is that the ultimate idea is that you're going to have a control plane that can either control real equipment, on this side, or else you can control an emulated environment. And the idea is that you swap within them. Okay, for example, you want to test something first, you test it on the emulator. Then you want to say, okay, it works fine on the emulator. Let's see how it works on the agent. Sorry, let's see how it works on the real testbed. And then it works well, you tweak it. And then once it works well, you can go back here. You're confident that now your Mininet optical is as good as the testbed. Now you go back here and you scale it to 1,000 nodes, which is something that you cannot do in the testbed. So that's very interesting. Now, in fairness, that's the way we built it. The way we built it was to have these testing control planes that then you can use in here. But now, once we have this, now we're thinking, well, this actually could become a digital twin. If you start building the intelligence on top, you can actually take these to start building models that get more and more close to the real behavior. And maybe, in 10 years, we'll have this controlling completely the testbed. Now, Mininet Optical, this just shows a graphic of what it is. We're planning to release it as open source within the next couple of months. So it should be out soon. But the idea is basically it's Mininet with another part, which is the optical network simulation. So this simulates the optical network impairments. And you can basically can create components, which are, for example, ROADMs, that amplifiers. The fiber itself is got non-linearities and all others, loss and other things, and the transmitters. And the idea is that your control plane can modify parameters on which they work. They can read information like power, signal to noise ratio, and then their behavior is simulated here in the physical layer. You can see it looks pretty similar on the way you would program a Mininet. Now, this is a sample use case. This is work that was carried out by Politecnico di Milano, an optical group in there. So they, independently of us, so they were doing work on machine learning, and they were building a quality of transmission estimation algorithm based on, I forgot now the name of that. This is one of the machine learning. So they're based on one of the machine learning algorithms. And they all did this by themselves over simulation, and basically they simulated the way you would light up different channels in an optical system, and then depending on which one you light up first, you get a certain different behavior of the optical signal to noise ratio. So because the system is highly nonlinear, if you start channel in the sequence 1, 5, 10, things behave in a certain way. If you start the channel in 10, 5, 1, the behavior can be quite different. So this basically randomly selects channels from 1 to 80. Every time it selects a channel, measures what's happening to all the channels. It repeats the operation about 2,500, 3,000 times through online learning. So that was the name. And then, it gets better and better. That's the idea. Now, this is based all on simulated data. Great. So basically what we decided, we put the project together through NGI Atlantic. And we said, why don't you guys now try to do this in the real testbed? And that's what the idea. So we put through our testbed together to start a simple topology. And we're basically at the moment, we're still running this. And of course, it's much more difficult because even reading the OSNR across a bunch of channels, here is just reading variables. Here is much more complicated, okay? Because there's the way you can measure OSNR is not straightforward. But ultimately, the idea is that you have a control plane. Now what we have is a control plane for the testbed, and then you have the control plane for Mininet, and they, in principle, they're doing the same thing, which is this high-level algorithm, but they're still doing it in different ways. And I think that one of the targets that we will have is, can we make these two really similar? Okay, can we do seamless switching within a network and an emulation? And up to a point is convenient because maybe you always have some kind of translator, but this is something that we're working on at the moment. Now, just to finish up, I mentioned the testbed that we have. So that testbed is called Open Island. We're still building it, but it's very similar to Cosmos in terms of concept. The only thing that it's in Ireland. That's the main difference. But it brings together a number of technologies. Mostly it brings together the optical layer, then has the wireless layer and the cloud layer. Sorry, the cloud and layer 2, layer 3 switching. Now, everything, as I mentioned before, is based on optical, on open interfaces. So it means that from the optical, we have all that open optical networking that I mentioned. So all open interface so that you can put your own control plane. At the wireless side, what we have is that software-defined radio based on open air interface and SRS software radio systems. Now, on top of that, we also have something that's proprietary, at least to start with. And these are the real commercial Open RAN implementation. So that's the one that you work with 7.2 splits. Again, these are commercial. But nonetheless, there's a lot of interesting research because they are open RAN. So it means that you can actually do a lot of, it has a lot of open APIs. So you can implement all your intelligent control system also on this proprietary base station. Okay, that's the advantage. And of course, everything goes back to the switch, the optical fiber switch. That means you can build a lot of different topology as you like. Now, interesting thing as well, we also got 100 megahertz of spectrum, 5G spectrum license on the upper and 77 band. It's a test license for 1 year, but still it's very interesting because now all of these basically are going to work on commercial type of frequencies. So you can really see how those frequencies specifically work and also work with normal handsets. So you don't have to go around with USRPs. You can just use a phone to make your tests. And the idea is that, to bring it also, this is our building just outside the Trinity College, which is part of inside this. It starts from this corner. But this is a normal, intersection. And the idea is to start doing also interesting work in there. Now, just to see there is international connectivity already with the testbed. We are already connected to a P4 testbed in the US. We are connected we have physical connectivity. We just have to figure out the VLANs, but we have a 10G connection to the Cosmos testbed, okay, as well. And we are, the two are kind of similar. So the idea is that you can run the same experiments on both network, or you can run one across. For example, if you want specific equipment on this side, then you need a data, then you're okay with a data plane going this way, and then you can use other equipment on this side. And yeah, so I'm not going to, just a bit late, so I'm not going to go into the details of the optical devices here, but there are just all open optical devices. There's about almost 2,000 kilometers of fiber to do a lot of different topologies. The wireless, as I mentioned, are based on USRPs. So the software is open air interface and SRS, but there's also going to be commercial Open RAN systems. And then the layer 2, it's pretty standard. We got, all virtualized, of course, but we got a number of servers. We have P4 capability. And also, of course, the virtual PON is going to be a highlight of the testbed because that's what we've been working for quite some time. The only thing that I want to see here is that, the power of the topological configuration, okay? Because every single component goes through dedicated fiber through this big fiber switch. It means you can really connect anything to anything else. Example, use case 1, you have Open RAN, 2 base stations. As the vendor says, you need to use point-to-point fiber to your DUCU servers, otherwise it's not going to work. That's the specification we have. Okay, so that's one way to do it. But we don't believe, and we see what if we can create the same latency and the same level, quality level of a point-to-point connection, we can do it with a passive optical network. And then, instead of terminating directly, going to even to 1 or 2 switches. Okay. And that's exactly what you do. So you reconfigure your switch to this topology, and then you can start doing your experiments in here. Okay. And then you can see, first of all, does it work or does it not work? But then there are also more subtle things, like, if you're controlling multiple base stations, if this solution works but increase the latency, you might not be able to do the coordination across the base station as well as here. Okay. So there are a lot of interesting research that can come up over here. Other example, we go towards 6G, we're going to have Terror's solution. If you try to digitize a Terror signal, it might not work that well. So another possible solution is that you modulate the Terror signal directly into the laser. So that's called analog radio over fiber connectivity, which is an intelligent and clever idea, but it suffers a lot from distances, interaction with other channels. So an interesting thing is that can you mix that thing with other channel in a highly heterogeneous network, like a passive optical network followed by a metro network. And these are all interesting things that we can do. So I just last slide for conclusion here. So I mean, just something to, there's a lot of information here, but something that maybe to take away is that disaggregation is really happening everywhere in the network, and the standardization is going very well, is moving forward, and we have great physical layer technology that can provide a lot of the optical layer flexibility. Okay. And I think there is a lot of interesting things that can come up with this convergence. Now, this I stole this from Dan. Dan tends to finish his presentation with this. I thought the same. And I mean, but that's, you can't put it any better, I think, that Dan does, is that, at the beginning, the story goes that, many years ago when people were trying to fly, the problem wasn't flying. Okay? The problem was controlling the airplane to avoid it crashing, because people could fly. So it's the same with our networks. I think today, especially with 5G, 5G has been sometimes we say, well, 5G doesn't look very different. So G is not changing much, but the actual RAN technology is pretty much as they promised. Okay, you can get 1.5 gigabit per second even on a small cells. So it's actually there. So the difference, what's missing is really the control of that. So how do you control that so that you can make the actual connection reliable, okay, by using more than one base station and all together, for example. So I think network virtualization and open networking has really opened up this possibility to analyze, research, and test these control planes, which is really, I think, where the challenges to come will be. And you can do that, as open that on the wireless, optical, cloud domains, but most importantly, jointly across this domain. Okay, the fact that now you can do the control across these domains, and that's critical because we've seen earlier on with the latency is of course critically, but I mean at the end there's no point if one part works and the other doesn't. Okay, it's a chain, so you need to get within a certain latency capacity from one end to the other. So joint control plane is really important if you look at those low latency and mission critical application. Second things, open testbeds, are essential because now you're really moving, especially into digital twin. So we had times where you could do machine learning over simulated data. That's kind of not an option anymore, right? So really, you need to make sure that this works today as we get close to the research gets close to be developed into the network. And the big question here, once you go into the machine learning, I think, is how much of this control can be given to AI? So can you build the perfect digital twin? Or even more, can that digital twin actually build itself to become that perfect digital twin? And here I finish my presentation. Thanks, everyone. I think I took a little bit more than an hour, but yeah, that was. I hope you saw it interesting. And if you have any question, please do let me know.